Hi, in this video we're going to talk about 4-byte autonomous system numbers on BGP. If you remember, we use the concept of an autonomous system. It's widely used in routing. It basically means all of our devices are under the control of the same organization. So, you are a company, you have your set of devices, they obviously have some routing configuration, you have some IGP, you have BGP, you have some routing policy, you have security policies, and they should all be pretty much the same all over your autonomous system. When using BGP, we have this concept of autonomous system, and we have numbers. And it's the way that we interact with other entities on, for example, the internet. Or, if you have a private implementation where you're using BGP, that's also a valid scenario, where basically you are two different companies, each one with the routing policies, but you need to exchange some routing information. So then you will use something like BGP. Since BGP is basically the protocol that maintains the internet, so it's a protocol that's used to build the internet, we have a lot of different companies, we have a lot of different entities, we have ISPs, we have large enterprises, we have not so large enterprise that are all connected using BGP. They have their own addressing space, whether it's IPv4 or IPv6, and using this concept of autonomous system numbers and using BGP, they announce that information to the world using a service provider or using a series of service providers, and that's how they're reachable. We know that, for example, some particular block of IP addresses, it's generated on autonomous system, whatever, 10,000, 20,000, doesn't matter the number. So, when BGP was created, we have the allocated space for those numbers was designed to be only 2 bytes. That's what we can see here. So we have 2 bytes. That gives us only 16,535 possible autonomous system numbers. The issue here is that obviously this is not sufficient to allocate all the demand and to continue to grow the internet, which just continues to grow more and more and more. So what was the strategy used here? This is kind of a similar, or we can share some parallels to the IPv4 address exhaustion, where we have this pool of IP addresses, but due to the internet and due to the size and due to continuous growth, the whole pool was exhausted, and now we need a strategy to continue to use the internet, and that's the result of IPv6. In here, the solution was that we would go from 2 bytes to 4 bytes. So with 4 bytes, we have now 32 bits of possible autonomous system numbers, which is quite a lot. We can see here. This is a number that, if you're familiar with IPv4, it will look it wouldn't look new. So that would be roughly around 4.2 billion possible autonomous system numbers, which is quite a lot. It means that this will resolve that issue, and we will have the possibility of having a lot of different companies, entities, service providers, universities, etc., having an autonomous system number. And this is a new way of doing a new way of allocating that to the public. So you might be thinking, okay, so great. So 2 bytes wasn't enough. Now we have 4 bytes, which looks to be enough for the foreseeable future. Who knows if we might need more, or if we're going to come up with something better than BGP to replace it. But for now, this will suffice that demand. So what happens now? What happens when we have 2 bytes and 4 bytes? Can we peer between each other? So yes, obviously with something the size of the internet, a compatibility strategy was needed. Some sort of way that we can define what would happen needed to be done. And it exists. Basically, we have this new way of supporting the 4-byte number is announced as a capability, and we have two attributes for that. And the two new attributes are AS4 path and AS4 aggregator, and we also have a reserved autonomous system number. I'm going to go into it in a second. So this means that if I am a large organization and I already have my autonomous system number and I don't need a new one, I can happily continue to use my 2-byte autonomous system and interact with other devices, interact with other clients or enterprises or universities that use a 4-byte system completely transparent. So there's some compatibility there, and it's by using that reserved autonomous system. So how does that look? Well, that will look like this. So we have two devices. You have, for example, let's say old, let's say new. So this would be 2 bytes, and this would be 4 bytes. So for example, I don't know, let's do a private one. So do 400 and something like that. So that would be our 2-byte autonomous system number. So 64,600. And our newer one, let's say it's 100,000. So that would be a new 4-byte autonomous system number. So what happens? So how do they form that session if the old one doesn't understand this? Because maybe it doesn't understand this, or it's using the 2-byte because it's part of a very large old organization that already had the autonomous system in the 2-byte format. Well, what will happen is, remember that they will send opens to each other. They will send open messages to form that session. When the new router sends that over to the old router, he will do an interesting thing. So remember that under normal circumstances, he will announce his timers, he will announce his autonomous system number, he will announce his capabilities. So this is exactly what's going to happen here. He's going to announce his autonomous system number as 2, 3, 4, 5, 6. Because he doesn't know if the old device would understand the 4 bytes. So as a kind of a compatibility mode, he will send that reserved autonomous system number of 2, 3, 4, 5, 6. And he will send the in that open, he will send the capability saying that I support 4 bytes, and my 4-byte autonomous system number is, I don't know, for example, the 100,000 that we have here. Since the old router won't understand the 4-byte autonomous system number, the session will come up using the 2, 3, 4, 5, 6. But since those attributes are optional transitive, it means that the old router will pass them along if he has other sessions, other BGP sessions established, which means that that could perfectly serve as a transit. So we will see now a capture to see if this actually happening on a packet capture. Let's look at it at a packet capture of this. So if we look at a packet capture here, we can see that we have, I should delete that. Let's delete that. We see that he's sending that open message. He's presenting his IS number as 23456, which is all normal. It's all normal for a 2-byte only BGP router. You would say, okay, so your autonomous system number is 23456. Awesome. But if you see here, we are advertising a capability that's defined as support for 4-octet AS number capability. And we can see here the value that we have. The value in this case is 65,537. That would be in AS dot notation, that would be 1.1. Since the numbers can be so large, there's actually two notations, well, there's 3 notations that are typically used for to represent this. So they're called AS plain, which basically means the old way of seeing it. So, if that was 100,000 and you're using AS plain, you will see it as 100,000. There is one that's called AS dot, which means that you will use this, they will basically, that 32-bit value will get separated into two 16-bit words. So that would mean that, for example, if your autonomous system was 100, you would see it as 0.100. And for example here, if your autonomous system number is 65,537, you would see it as 1.1. And the maximum would be 65,300, that's not 300, it's 500. Would be 65,535 dot 65,535. And the other one, the final one, is AS dot plus, which basically means for all for 2-byte autonomous systems, you're going to show them like that. And for the 4-byte autonomous system numbers, you're going to show them like this. So it's kind of a mix of those. If you're using Cisco, that will be the default. If you don't change it, that's the one you will see. You will see that for 2 bytes, you will see it as you have seen them your entire life. And for the 4 bytes, you will get this new format of AS dot. So, for example, the one that we're seeing here in the packet capture will be 1.1, as expected. It's just preference, just a way, because obviously we're talking about 100,000, but you could have an autonomous system number easily of 25 millions or whatever, and that would be a very large number. So this is a way of simplifying it so the outputs are a little bit more readable. So it's nothing mystical. It's just a way of kind of slimming down a little bit those numbers. So instead of the 25 millions, you will see something like 10,000 dot 15,000. That obviously is not accurate, but it's just random number. There are calculators and there are converters that you can use. They're online, so you could use them to, if you want to, if you see it in one format and you want to see what it is in the other one, you can easily convert them, or you can do, some basic math there to do it as well. But just in case you were wondering why I was talking about 1.1s, and our diagrams also use that notation. So they use the AS dot notation, so we'll see 5.5 and 2.2. So in case you were wondering what that is, it's basically a way of writing the autonomous system number. Okay, so we can see there, for when we speak with 2 bytes, we basically just announce the capability. The 2-byte router doesn't have to understand it. He will just pass that information along, and we will be able to see it as transit. So let's look at this from a larger diagram, so we can talk about it a little bit more. So let's look at this diagram, and let's look at a prefix generated from, say, this device here, router 5. So router 5 is obviously using the 4-byte syntax, and we can see there. We can see there that format. We can see that 5.5. We can see that we also have router 1 and router 2 that are also 4 bytes. Router 3 and router 4 are 2 bytes. So we can write that up quickly. We can say here 4, 4, 2, 2, 4. Okay, so same thing will happen here. Router 5 will send that open. He will be doing the same thing that we saw in the packet capture, where he will be announcing. He will be announcing that information in the packet capture, where he will be saying, oh, my AS number is the reserve number, so 2, 3, 4, 5, 6. And he will also be announcing that 4-byte capability with his actual autonomous system number of 5.5. Since router 4, doesn't understand this, he will just form a session with router 5 on autonomous, assuming and thinking that router 5 lives in the autonomous system 2, 3, 4, 5, 6. And that's completely fine. So when router 5 sends that information over to router 4, the AS path will have that number in it. So, the prefix was originated in that particular autonomous system. Great, but even though router 4 cannot use it and doesn't understand it, we will still include that that 5.5. So 5.5. It will still be included in the IS4 path, or as in the packet captures of the show, new IS path. When that information goes from 4 to 3, we will see that the IS path now is going to be 400 and 2, 3, 4, 5, 6. The new IS path, or the IS4 path, will remain to be 5.5. So remember, that information is going to be optional and transitive. Optional meaning that it doesn't have to be understood, but it will be, and transitive will be sent out in the information. When that information, the same thing will happen when that information goes over to router 2. The S path there will be 300, 400, and 2, 3, 4, 5, 6. Only that now router 2 does understand this. He understands what the actual path is, and you will be able to see it on that device. So you will be able to see that the actual AS path for that particular route, for whatever information it's been generated, it's been announced on 5.5 that the correct IS path for this is 300, 400, and 5.5, because router 2 understands 4 bytes BGP IS numbers. So the interesting thing happens here when we send the information over to router 1. We no longer have this compatibility issue. He knows that router 1 understands the 4 bytes. He understands 4 bytes. So the IS path here will be 2.2, 300, 400, 5.1. And we will see, or we will be doing, this is how that information is going to be propagated. We can see here that it's compatible. We can, have those two devices interact as expected, and they can live like that without needing to be migrated. And we can continue to add 4-byte organizations, 4-byte universities, 4-byte autonomous systems, until, obviously those 2 bytes are phased out because they are migrated to the new format, or they're deprecated, whatever we need. So this allows the internet to continue to grow. So let's look at, we look at this in the diagram. We talk about how this will look like in the diagram. Let's look at packet captures. So you can see this actually on, on updates between the devices. So let's look for 5 and 4. So we look at 5 and 4. We'll see here the update message. We'll see here, let me try to center that a little bit. We see here that we have this new AS path, which is the AS4 path, and we have here the number in AS plane. That will be, we made that AS plane, it will be 5.5. If we made that to AS dot, sorry. In AS plane is 327,000, etc. We can see here optional, transitive. If we look at the AS path, so here one AS path. If we look at the AS path, we have that reserve number that is used for compatibility. That it's a number and it's an AS path format that will be understood by router 4. Right. So Let's now take a look at router 3 to router 2. Because if we look at router 4 to router 3, it will be exactly the same thing. There won't be any difference there, like I said in the drawing. We'll just see that we now have the number of router 4 in the IS path. We can still see this in the update between 3 and 2. So this will go from 3 to router 2, and we can see now that we have the initial number that's used for compatibility. We have 400, which is the autonomous system of router 4, and we have 300, which is the autonomous system of router 3, as expected. If we see the new AS path, which is the AS4 path, we can see that it's unchanged, just as we saw in the diagram. We have it here in AS plane, in AS dot notation, that will be 5.5. So let's now look at the interesting bit, which is how when this gets sent over to router 2 to router 1. When this gets sent over to router 2 to router 1, like we said, now there's no need to have that, that compatibility weirdness that we saw, or compatibility that we have between 2 and 4. We now have that the AS path, the 2, 3, 4, 5, 6 has been replaced because router 2 knows that router 1 will understand it. So since that was replaced, we can see it here just like we saw it on the diagram. The old reserve number has been replaced by the 4-byte number to give router 1 the clear actual path that prefix has gone through, and to give it the accurate view. And we can see it here. So this would be in AS plain notation, and in AS dot it will be 5.5. Then we have 400, 300. This would be 2.2. And router 1 basically gets the absolute, or gets, like I mentioned before, the correct view on what the actual AS path for that particular prefix or NLRI information, regardless of the fact that it has gone through 2-byte devices that obviously we had to apply that compatibility. And basically, this is how we are continuing to grow. We are able to continue to grow the internet. We are able to continue to provide companies and organizations that require an autonomous system number. Because remember, if you require an autonomous system number, it basically means that you have prefixes, whether in IPv4 or IPv6, that are owned by your organization, and you want to announce them to the world. You want to announce them to other peers. You have multiple connections with multiple providers, and this is the way that you do it. And this compatibility mode ensures that we can coexist with the old way, with the old notation, while the 4-byte gathers more momentum, and eventually if it doesn't replace completely the 2 bytes, it will surely we will have more 4-byte autonomous system numbers than 2 bytes. I hope this information has been useful. Thank you for watching.